Hello everyone, can you hear me at the back? Okay, cool. This next talk is by Stephanie Yardley. She's a postdoctoral research fellow in space weather based at UCL's Merlot Space Science Laboratory. The talk is called Observing Sun from Space.
Thank you very much. Can everyone hear me? Yeah, you're all with me this morning. Sorry for the delay. We had a few technical issues as what happens here, particularly at live conferences. In fact, this is the first live talk with an audience that I've given since August last year. So I'm really actually pleased to see some faces in the audience. And so today I'm going to talk about observing the sun from space. So hopefully I'm going to do two things. I'm going to convince you that one, the sun is very interesting and that we should study it. And two, why we should also go into space to study the sun. So why we should send satellites or spacecraft into space, because obviously we can also observe the sun or other stars from the ground as well with ground-based telescopes. So I'm going to convince you why we do that and why it's important to study our sun, because it affects us here on Earth on a daily basis. And what I always like to show at the beginning is here you'll see a lovely movie of the sun. This is what the sun's been up to the last 48 hours. And you might be able to see some really interesting features on here. So we have some bright patches here. We have an eruption from the sun. I'll talk about those a bit more later. So you can see the sun is really, really interesting and dynamic and changes over seconds or minute timescales. So what I like to do first is to start from the visible surface of the sun. So this is the visible surface that you can see with your eyes. Now, please never look directly at the sun with your eyes. I always have to put that in there because it may seem obvious, but please do not do it. And most astronomers would think, oh, the sun's pretty boring. It's a main sequence star. It's not really that interesting. But when you start looking at the sun, you start to see features like this one, in the centre here, this lovely dark patch here. And these are sunspots. And these are all due to the sun's magnetic field. So this is what makes the sun interesting. It's its magnetic field. And this is where all our activity, our solar activity, comes from. So these are called sunspots. They appear as dark patches on the surface. They're regions of very intense magnetic field. So this is on the sun's surface called the photosphere. But what we can do when we go to space, so this we can observe from the ground, we can see optical light from the ground, but if we want to look at different wavelengths, and look at the sun in different wavelengths, then we really need to go above the Earth's atmosphere because this blocks out light such as UV, which is a very interesting wavelength to look at the sun in, and I'll show you why now. So you can actually start looking at the sun in different wavelengths, seeing different layers. So here's the photosphere. That's like the magnetic footprint on the surface, so the magnetic fields. Back to the sunspot. Here we go to the chromosphere. So this is 30,000 degrees. You can start seeing these different structures, these bright loops here. And then we go out into the outer atmosphere of the sun. And this is the solar corona. And we're actually looking at plasma here that is millions of degrees. So we can go all the way from the surface and look through all the various layers of the sun's atmosphere and look at all the different structures at different temperatures by using different wavelengths. So we can look across the entirety of the electromagnetic spectrum, which is something we can't do from the ground. And I must admit the sun does look pretty impressive in ultraviolet light. This is the sun today, so this was actually 7:30 this morning. That's the closest I could get it to this time. But we've got satellites up there all the time looking at the sun. With this particular satellite, so this was from the Solar Dynamics Observatory, we can take images of the sun every 12 seconds. So we get an image like this every 12 seconds. And in fact, there's even an app on your phone that you can get, and you can, if you're really that addicted like I am, you can just look at the sun on there in all the different wavelengths, which is what I've been doing quite a lot at the moment, and I'll explain why it is later in my talk. But you can see the sun's actually quite interesting at the moment. The sun's finally woken up, and this is because the sun has a cycle, an activity cycle. And again, I'll talk about this slightly later on. So here we get to our first movie. So I just want to show you the regions that emerge on the surface of the sun. So these are what we call active regions, and these are the loops that are associated with these sunspots that you get on the surface. So this is essentially the magnetic field breaking through the surface of the sun. And what you see here is you see that there's a coupling effect. So you have the plasma, or the hot gas of the sun, actually traces the magnetic field, because we don't actually see the magnetic field itself with our eyes. You can think of it as like a bar magnet, or I don't know whether any of you back in school got the magnets out with the iron filings, and you can trace the magnetic field, and then someone always got the iron filing stuck to the magnet and ruined it. But this is exactly what happens on the sun. So you get these regions, and you can imagine like a bar magnet, and then you get these loops of very hot plasma tracing the magnetic field. And now I just want to zoom in onto the surface to show you the size of these sunspots, the size of these things. And we'll keep zooming in, and you can start to see some of the beautiful detail of not only the sun's surface, but also sunspots. So these are actually humongous structures. I can actually put the Earth on there. So you can see that these are as large as the Earth, if not bigger. In fact, sometimes we get sunspots that are as big as Jupiter. Yeah?
Sorry, what are the units?
What are the units? So this is something we use arc seconds. So it's more like an angular unit, but you get, I think 1 arc second is around 750 kilometres. So these cells are thousands of kilometres across that you're looking at. So these are convection cells that bubble on the surface. And then you have these sunspots here, these dark sunspots where you get these really intense magnetic fields. So the sun is, yes, very interesting, very dynamic, changes on timescales of seconds to minutes, but also months as well, as you'll see. So the sun has its own cycle, the solar cycle. This is roughly, as you'll see, 11 years in length. And this just basically determines the activity of the star. So what you'll see is, this is quite an old solar cycle now, but if you look back in 1996, you'll see that the sun looks very bare. There's not many features on it. And this is because it's during minimum. Basically, the sun is asleep. So there's not many of these sunspots on the surface. You don't see the effect of the magnetic field so much. It's just very quiet and asleep, essentially. And you don't really get much activity from the sun during these periods. But as you see, as time goes on, you'll see that there's more of these bright features, these loops that are in the outer atmosphere, in the corona, and you can see that the sun gets a lot more interesting, and you can see all these loops on the surface where you get a lot of the sun's activity. So this is what we call solar maximum, and this is when the sun is awake. It starts throwing stuff at us. We get a bit scared. You'll see it a lot in the papers, as I'll show you later on. And so we've been observing the sun for, well, we've actually been observing the sun for centuries, but the records that we have are only back to about 400 years. So essentially this is just showing you the number of sunspots on the surface of the sun. So we get someone that's observing the sun and notes down the number of sunspots versus time. And this here shows you this 11-year cycle, so you can see the sinusoidal variation of the cycle. So when we have lots of sunspots on the surface, this is when we get lots of solar activity. And then when we have less sunspots on the surface, this is when things go quiet. And you can see that there's also some larger trends. Whether these are true trends or not is something that's quite widely debated, because one observer can't live for 400 years. So there could be inaccuracies due to the way that people measure sunspots, the sunspot number on the surface. So there's been a lot of work that's been done on this to actually figure out whether these, say like the Maunder minimum, is actually a true minimum, because there's a lot of hearsay about this corresponding to an ice age, and whether that's actually true, that's quite controversial. But this is what the sun does on an 11-year basis, on a 100-year basis. So it's constantly changing, and the sunspots are constantly changing on the surface. So this is our current solar cycle. So we name them to keep track of them. So we're currently on solar cycle 25. And what quite a few physicists do is loads of people create models, they look at the observations, and they try and predict what the sun's going to do. Is it going to be a strong cycle, loads of sunspots on the surface, is it going to be weak? So you can actually see 2 cycles ago, 23 was quite a strong cycle. You've got a sunspot number of over, 170, 180 there. But then as you're getting towards the present day, so the last solar cycle 24 was extremely weak. It was probably the weakest we've seen in 100 years. And now we're on solar cycle 25. So some scientists got together, I think, I can't remember what year it was, 2018, 2019, and decided by looking at the models and looking at the evidence that we had, what the sun was going to do, when the next cycle was going to start, when is the sun going to wake up and come out of minimum. So they actually predicted that it would be April 2020, plus or minus 6 months, and that it will have a peak in July 2025 of around 115. So again, this is quite a weak cycle, very similar to our last cycle. But this changes all the time. So, for example, what you'll see in a minute is we actually reached solar minimum before April 2020. And here's the actual data to show this and some more predictions. So we actually went through minimum in December 2019. So that was roughly almost 6 months before we expected. And now the race is on to see which model or which prediction is right, whether some of the stronger predictions are right or whether the one that the panel made back a couple of years ago is correct. And at the moment, it's looking that it might be a stronger cycle than we expected. So we might see more activity than we expected, and we might actually get more of a normal cycle. But it's still not as strong as some of the cycles we've seen in the past. And again, this is something that scientists want to know more about. Why are we getting these weaker cycles? Can we predict what's going to happen the next cycle, cycle 26? Is this going to be strong? Is it going to be another weak cycle? Who knows? But all we can do is rely on the observations and the models we have. These can always be improved. So now I'm going to show you some of the interesting solar activity that occurs on the sun. So here what you're watching is another movie in ultraviolet light. And this is actually a solar flare. And this is just a sudden, intense, bright light on the sun. They usually emit across the entire electromagnetic spectrum. And the energy in one of these events is probably the same as about 100 megaton hydrogen bombs. So it's a huge explosion that happens on the sun. And it transfers energy. So we get energy in terms of particle acceleration, which you'll see here. So you see this snowstorm effect on the satellite. So that's all the particles that are being accelerated hitting the detector. So we see that as a snowstorm effect. So these are certain activity. As you'll see, there's a whole range of activity from our sun that can cause us beautiful displays of the aurora, but also can cause us some problems with our technology as well. We have what is called coronal mass ejections, and these are just these eruptions that I was talking about earlier, so eruptions of magnetized plasma from the sun. And you can see a very interesting period here around, it's quite a long time ago now, 2003, but these were called the Halloween storms because they're around the 31st of October. And what you can see here is we've got a space-based satellite and we've created an artificial eclipse. So we've blocked out the surface of the sun. So normally we can't see the corona. The corona is quite faint in emission. So we block out the surface of the sun. And then this means we can see the surrounding structure, and then we can see these eruptions that travel out into space. And these eruptions can travel at several million miles an hour. They can head straight towards us and hit us here on Earth, which is, again, problematic, and I'll describe why in a moment. And they vary with the solar cycle. So you can see, say, 6 or 8 of these per day when we get to maximum, which is where we're heading now. And then during the quieter times, you might see 1 or 2 per day. So we're really getting excited what we'll see in the next couple of years with the solar cycle ramping up and activity ramping up. We can then make really nice movies such as this. So this is from the Stereo spacecraft, and these were 2 spacecraft that were sent, I think it was around 2006, 2007, to basically go behind the sun to give us a 360-degree view of the sun. And so what you'll see here is if you squint and look close enough, this is actually the sun at the centre. And then we have a little white dot here, which is the Earth. And so what you can see is along the Sun-Earth line, we're watching essentially what comes out, so particles, eruptions that come out from the sun and are going into space and are hitting us here at Earth. And I think this is probably one of my most favourite movies of watching particles and eruptions come from the sun, because you can literally trace it all the way from near the sun, a couple of solar radii out, all the way looking at our planet, other planets, and other solar system bodies out there. So when these eruptions arrive, luckily for us, we've got our own magnetic field. So although it interacts with our magnetic field, we're mainly protected. Otherwise, we wouldn't be here now. We wouldn't be alive. But also, even now, while I'm talking to you, we're being buffeted by particles from the sun. So this magnetic field protects us. And what actually happens when one of these eruptions hits the front side of the Earth, so you can see it happening here, the magnetic fields interact and you kind of get this onion peeling effect and a build-up on the other side. And then this eventually leads to, it's almost like the snapping of elastic band, and then you get particles that get accelerated down towards the Earth in the Earth's atmosphere. And this is when you get stunning displays of the aurora. So there are many types of activity from the sun that can cause the aurora and cause storms in our upper Earth's atmosphere. And hopefully, have any of you seen the aurora? No. Oh, a couple of you, yeah. I'm sure you'll say, go see it. Because the first time I saw the aurora, particularly for someone studying something like this, I was speechless. But if you get the opportunity, really, really go and see it. But you can see here we've got, in the top, we've got a movie taken from the International Space Station. So this is looking at different perspective. And you can see all the beautiful structures, all the different colours, so the greens, the reds. It really does give a beautiful display. So I guess that's one of the nice things about all this activity that's coming from the sun our way. However, there is a downside, and one of the reasons why I'm interested as well is a lot of these eruptions, for example, or the particles can cause a lot of problems with our technology, particularly because now we're becoming more and more dependent upon our technology on a daily basis. So it can cause problems with satellites, we can get problems with radio communications, GPS signals can go awry, we can get ground-induced currents. These affect things like the national grid, so the power, so you can get power outages. So anything to do with communications. Also, if you're if you're on a spacecraft, whether that's, space flight in space or, whether you're on an aeroplane, it increases the radiation doses you receive. So what we really want to do is we want to be able to, and what I do on a daily basis, is to understand more about the sun's evolution and what happens on the sun and these sunspot regions, to try and predict when they're going to erupt or when they're going to send us these types of events, so we can kind of mitigate the damage done to our technological systems. And as an example, at the moment, the National Grid want a 5-day warning, and we're like, we can't give you a 5-day warning of that, it's impossible. But we are really trying to use observations and, along with our models that we have, to try and predict what the sun's going to do in the next couple of days. And so some of these spacecraft we use and some of the observations that I touched briefly on to make these predictions are, for example, we've got this. So the coronagraph earlier I showed with the eruptions. This is the SOHO coronagraph. And this is an amazing mission because it was meant to last 2 years and it's going 22 years later. So we really depend on that to see what's coming towards Earth. So that's sitting just above Earth, along with the Solar Dynamics Observatory, which gives us these beautiful images of the sun in many wavelengths every 12 seconds. But then we also have the stereo spacecraft. So we have one's called ahead, one's called behind, mainly because of how they orbit ahead and behind the Earth. And roughly around 2011, 2013, we had this great 360-degree view of the sun, because we always want to know what's coming round. because if we know what's coming around, we know what might be on, might rotate into the Earth view and then might cause problems for us and might send an eruption our way. So this is really important. Unfortunately, we've lost stereo B now, but we've still got stereo A. And this was a couple of days ago, so this just shows you all the positions of the spacecraft and also the inner planets. So you'll see here's stereo A, so this is still going, and the position it's in at the moment, it gives us an idea of what's coming, what's rotating around on the sun. Have we got any large sunspot regions? Stereo B, unfortunately, we can't talk to, but we also have some more exciting missions that I'll talk to you about later. So we've got Solar Orbiter, you can see is getting very close into the sun, and Parker Solar Probe, which is currently inside the orbit of Mercury. And it's very difficult to make spacecraft that can survive these kind of conditions. So it's a very, very exciting time to be in solar physics and to study the sun. We have so many spacecraft up there monitoring the sun, monitoring the Earth and the Earth's magnetic field and what's going on there, and also in space. So we have things like the Voyager spacecraft that's past the Sun-Earth system now and is out into interplanetary space. That's been going for decades now. We have many spacecraft like the Stereo I've talked about. Hinode is a Japanese one that we use. But there's also Solar Orbiter, which was launched just before COVID. I think it was February 2020 it went up. And also Parker Solar Probe, which is an American probe that's up there as well. And then we have all the spacecraft also monitoring the Earth. We call it the magnetosphere, so the Earth's magnetic field, and also the atmosphere. And so now I'm just going to take a few minutes to talk about Solar Orbiter, which is a particularly exciting mission. As I said, it launched back in February. And I was actually lucky enough to be there. So I went to Florida, Cape Canaveral, to NASA, lucky enough to be invited. And this was the launch from about 3 miles away. And it was a very nail-biting moment because people had spent their whole careers working on this satellite, and we really didn't want it to blow up on the way up there. So there was a lot of nervous energy, a lot of excitement. It was a night launch, which is really cool. But yeah, it was just incredible to see this spacecraft, a spacecraft that I will be using data from in the future, launch. And then obviously we had to wait a year or two for it to get closer to the sun to be able to see the data from it. So again, if you ever get to go see a launch, we'll get to go to Cape Canaveral and go to the Kennedy Space Center. It is an amazing experience. So that was my last trip before we obviously couldn't travel anywhere, so it was quite a good trip to go on. And this is just a lovely picture from Cocoa Beach, and here you can see the trail of the rocket as it's going into space. I think that's one of my favourite pictures from the launch. And Solar Orbiter is a very interesting spacecraft because not only is it going to get very close to the sun and image the sun very closely, so we're going to do a lot of connection science, so where we stare at the sun but also measure what's hitting the spacecraft. So that's going to be a big thing for Solar Orbiter. And it will get very close inside the orbit of Mercury, so we'll get a very close-up view of the sun that we haven't had before. But also, later in its mission, its orbit is going to start to incline. So it's got a very interesting orbit with lots of planetary assists, so using Venus, using Earth to get up there. And what it will do is its orbit will actually incline and it will start to look at the poles. And we don't really have any, we've never had any images of the poles before. And stuff like that is going to really help with these models, which help us predict what the sun's going to do and what the next solar cycle is going to be like. So, but unfortunately, we've got to wait to, I think it's 2025, 2027 until we're going to be up at the poles. But for now, we're just going to look really close into the sun and see what we can see. So I just want to highlight a couple of things that have been in the news recently or what we've seen recently to do with solar physics. So some of you may have seen this. Did anyone see this in the news about SpaceX? Yeah, I can see a couple of you. So yeah, so SpaceX decided to launch 49 satellites, and what they didn't realise is that the sun was erupting quite a bit at the time. So they saw one eruption happen from the sun, that hit the Earth, and then that passed and that was fine. But then when they launched the rocket with all the satellites on, with the Starlink satellites on, then a couple of more eruptions came from the sun, and then they impacted Earth and impacted the atmosphere. And what happens is the Earth's atmosphere heats up, and then this increases the friction and the drag in the atmosphere, so then it causes the satellites to fall. And this is what they weren't planning for and weren't expecting. So this shows you why it's interesting and why we need to monitor the sun and monitor what we call space weather. So these are all the changing conditions near the Earth that are caused by anything that comes from the sun. So I thought that was interesting that we found. I think that was back last month in February. And then hopefully you can see this. I can't tell whether you can see this with contrast very well. But the same region that produced these eruptions that then affected the Starlink satellites, we caught with Solar Orbiter. So this is a beautiful image and one of the first images we've seen from Solar Orbiter. And you can see this huge eruption coming out from the sun there. And this was the same region that affected the Starlink satellites. And then finally, still talking about Solar Orbiter, I have the very exciting experience. It's been quite a stressful, nervous and exciting experience of planning some of the first observations. So telling this satellite where to actually point and what to point at the sun, because it's not necessarily, not all the instruments are full sun images. So here you can see actually the field of view of the instruments, and this is the region, the active region on the sun that we're currently looking at. So while I'm talking to you now, Solar Orbiter is taking these observations, hence why I can't actually show you the Solar Orbiter images. I can only show you the SDO image and what we'll be looking at with Solar Orbiter. So I've been in a lot of meetings with ESA and others trying to tell Solar Orbiter where to point, and I can definitely say it's a career highlight so far. So fingers crossed that we actually get some good data. And then in a couple of weeks, I'll have the same job again. So fingers crossed we get something that we can analyse and get some really good data. And then finally, I just wanted to finish off. We talked a lot about observing the sun from space. I wanted to show you a movie from one of the ground-based telescopes. And this is one of the recent telescopes, the Daniel K. Inouye Solar Telescope, or DKIST. And I'm not sure whether this is even going to play because the movie is so large, because it's so high resolution, that it will struggle to play. But you can see that we can see this is the surface of the sun again. You can see these convection cells in such amazing detail. And this is because on the ground, we can build these huge telescopes this is 4 meters in size. And you physically can't send a 4-meter telescope up into space because it's too heavy, and every kilogram costs about £10,000 to £20,000 to send up into space. But you can get beautiful images like this, and DKIST has only just come into operation now, and so we're just starting to get the first science data and the first science images. So this is actually the first image of a sunspot taken from DKIST. So DKIST is actually in Hawaii. Hopefully I get to visit DKIST in Hawaii. That's the dream. You always want to go to the conferences or to the telescopes that are in the nice places. But you can just see the stunning detail of this image. So I really can't wait to see what comes out of DKIST in the next couple of years. And with that, I'll finish there and then invite any questions if anyone has any.
Thank you so much for that amazing talk. Right now, there's no questions online, so if anyone watching does have any, just send them through and I can access them and ask. But right now, we're taking questions from the audience, so does anyone have any? I'm going to run up quick.
Thank you for that. My name's Shaq. I work for the Shetland Space Centre. I was reading about the Parker probe and its close pass by the sun. I was just curious to see if you could explain what the benefits of that was and how the mission went.
Yeah, so it's still going on. I think it was its 11th pass close to the sun. And a lot of the time, to really understand what's going on at the sun or in the sun's layers, you actually have to be there. So what Parker Solar Probe has done and is doing is literally flying through the corona, flying through the outer atmosphere of the sun, which seems crazy. How can it do that when it's so hot? And that's how we can understand a lot about the structure of the corona. So a lot about what the magnetic field's doing, a lot about what the plasma's doing. And what we're finding, and as I've said during the talk, things change, things evolve over timescales of seconds, minutes. And so you really need those high resolution data sets right there, right in the sun. And they're starting to discover things and phenomena that happen in the atmosphere that we might not be able to see further out or with less time resolution as such. So yeah, so the thing it's done is flown through the corona for the first time. So it's pretty exciting stuff.
Awesome, thank you. Has anyone else got a question?
Thanks for the really interesting talk. You mentioned the 11-year solar cycle. What's the current understanding of what causes the ups and downs?
Yeah, so it's all to do with the magnetic field that we think. The problem is we can't observe inside the sun. So we have to infer what happens in the sun with models, with what we see from, say, waves that propagate through the sun. And so what we think happens is the sun has a magnetic field, which is it's below the surface, so in the convection zone, the tachocline around there. And what happens is the sun's magnetic field, it winds up, and as it winds and gets stretched, it starts breaking through the surface. And that's what happens over the solar cycle. And then once all these regions of the magnetic field are broken through, it then kind of calms down again. So it's all to do with the winding of the magnetic field inside the sun. And this is all to do with the rotation of the sun. So the sun doesn't rotate like the Earth. It rotates differentially. So at the equator, it rotates faster, 24 or 27 days. And then the poles, it's 35 days. So this is where you get this dragging effect. So the plasma drags the magnetic field, and then that causes changes in the magnetic field, and this is how we get the cycle. And that's the general, I mean, it's a lot deeper than that, but that's the general understanding of what we think happens inside the sun. And this is why we use models, any observations we can, to try and figure out how the solar cycle works, so then we can try and predict what's going to happen in the future.
This is a bit of a long walk, 1 second.
So the probe has to send information from close to the sun all the way back to Earth. Wouldn't things like the electromagnetic field or the radiation from the sun affect the quality of the information received?
So you have to, not really, but what you have to do is you have to be careful of how you build your spacecraft. So obviously the spacecraft has to survive to send the information down. And this is where we use certain materials to make sure that it survives plus 500 degrees or whatever. The main problem that we have at the moment, say with Solar Orbiter, for example, is the way that the mission orbits. You might go behind the sun and you can't communicate the information back. So you might have to wait up to 6 months to get the data down. So this is something we're actively dealing with that we don't normally have an issue with. Normally, a satellite will just sit above the Earth and we just downlink the data almost immediately. But now we're having to think ahead. So like when I was talking about those observations, I have to plan 3 days ahead what the solar orbiter is going to look at. And of course, the sun changes within 3 days. So you have to, it's like an educated guess. So there's a lot that goes into thinking about, particularly now we're getting towards more interesting and more daring missions. It becomes a lot more complicated to get the information to the ground, and not just get it to the ground, how much you can actually store on board as well. There's a limit. So there's a lot of conversations between instrument teams. For example, there's 10 instruments on board Solar Orbiter. So you think of all the people involved that are having to have these conversations about how much data they can store without upsetting the other instrument teams or going overboard, and not overwriting data as well. So it's very, very complicated, and this is why it's left to the engineers and not to someone like me to decide how these things work.
Hello. So it's kind of like a generic question. So if I'm not like mistaken, I think the lifetime of the sun is just like approximately 8 billion years. So are we like working on something like after that, or do we have like any vision or something like what will happen next?
Oh, what can happen next to the sun? So it's halfway through its lifetime at the moment, and then eventually it will start evolving like a main sequence star does. So it will become very puffed up. It will become a red giant, and then eventually you'll just be left with a little white dwarf remnant. And so it will basically fade into the background. But when it does eventually explode, then it could probably engulf the Earth. The problem is we won't be around to care about this. So for the moment, yes, the sun will get hotter, it will get brighter, it will start to expand, but this is on a timescale of hundreds of thousands of years. At the moment, probably the evolution that we're most interested in is stuff like this, that it sends out eruptions or particles that impact us on a daily basis. And these kind of regions that they come from evolve from like minutes to weeks, months. So that I think, although I guess astronomers will be studying the life cycle of stars, and the thing is, by looking at the sun, you can learn a lot about main sequence stars, because the sun's a main sequence star, and this is probably the most common type of stars out there. So you can learn a lot from the sun that you can then apply to other stars. So for example, we think, so other stars are magnetic as well. They have stronger magnetic fields than the sun. So the types of flares and eruptions they send out compared to our sun are orders of magnitude bigger and worse. So it's interesting to study the sun because we can't necessarily directly image a star in that detail to see these eruptions. We can infer them from, say, like the light curves. We can actually look at light curves like exoplanets and see if there's any dark spots like these really big sunspots on the surface. But there's a lot more we can tell from our sun and the life cycle of our sun, and then apply that to other stars that are very similar.
Thank you.
Thank you for the very interesting talk. I have two questions. What was the Sun app that you mentioned?
What was the, sorry?
The Sun app, where you can look at the sun in real time.
Oh, the Sun app. I think it's like the SDO or the Sun Now. Just ask me later and I can show you the app. But you can literally load the sun in, I can't remember, it's 8 different wavelengths, and just click on it and see what the sun looks like now. Which is what I've been using a lot whilst doing these observations. What's the sun doing? Has it done anything interesting? Please do what I want it to do while I've got this observing time. Thank you.
Thank you. And my other question was, you mentioned how the same region did like a flare, but how do you get like GPS on the sun? Like, what's your reference points?
Oh, so how do you...
how do you know it's the same region?
How do you know it's the same region? So we know, I mean, most of the time, if we're lucky, we have other satellites that are looking behind the sun, so we can just follow it, follow the region. We generally know, because we know the rotation of the sun, we know how long it will take to come back round. The only thing we don't know is whether it's survived or not. So like these sunspots, they can live for days. So by the time the sun rotates all the way back round, it'll have decayed and it'll be gone. But some of the sunspots live for months, and you see them they're huge and they live for like many rotations. And then therefore they can produce eruptions on many rotations. This one we could kind of see because you could just about see it in the solar orbiter field of view. But another thing we like to use is something called helioseismology. So it's looking at, it's almost like seismic waves. We're looking at the waves of the sun. And we can actually use those to make maps behind the sun. So where there might be like large sunspots, we can see in these maps. So we can tell if we're going to see a large sunspot. So something could emerge on the far side, on the back side of the sun. We might see something in these maps. We don't see the detail, but we know something's there. And then a huge sunspot pops into view. But the main thing we want is to have these spacecraft all, looking at different angles or different views of the sun, because then that's when we can really see what's coming. And in fact, there's a satellite which was, I don't know whether any of you have heard of it, but it was called Lagrange that they're building. It's now called Vigil. It was, I think, renamed via social media. And that's going to sit at one of the, they call them the Lagrange points. And it's going to sit basically at L5, which is almost where stereo A is, probably a bit further, so you can see what's coming round, because those are the regions we'll be most interested in, that will produce eruptions whilst facing the Earth, and then we'll send them towards us. Because a lot of the other regions say rotating to the far side, we're not interested in. We're interested in what's coming round that will be at the centre from our field, from our point of view, and then will hit us and then cause all these problems with our technology. And that actually costs millions of billions of pounds. So it is, I mean, I think Elon Musk might have lost $50 million because of that. So, and these are just, you know, small Starlink satellites. You think what it can do if you have a power outage or something for 6 or 9 hours, which has happened before. There was a power outage in Quebec, Canada in 1989 for about 9 hours, and that was millions of billions of pounds gone. So this is why we're interested in knowing what's coming around the sun, what's going to be there, so we can predict and say, well, maybe we will see one of these huge eruptions in a couple of days that will then hit Earth.
Thank you very much.
Are there any other questions? Oh, okay, you again.
I thought I'd just ask around the satellite side, because the space industry's, you know, last year, 90% of satellites put up or more were small sats, more for observation, we want more data. But obviously the sun's getting more active, and Elon obviously paid a heavy price for that one. You know, probably small change to him, but still quite a big loss for his operation. But do you see more solar activity causing impact to satellites, and with the launch cadences increasing over the number of years, especially in the UK, you know, launchers having to be more careful about when they launch, and satellite operators about how they operate in space?
That's a really interesting question. I'm not even sure whether someone's done a study about that. So if someone wants to do a study, I think it'd be really interesting. And I think what you're going to see is, obviously there's going to be more problems, or at least people are going to be more aware of what's going on. I mean, clearly Elon was aware that there is space weather, but the problem is we can forecast these things and we can have a miss, or we can be wrong, or we cannot forecast something and we get something that hits us. So it's very difficult right now to give extremely reliable forecasts. It's like forecasting the weather. You say it's going to rain outside, and then it's beautiful sunshine all day. And we can do just about as well as that, maybe, if we try really hard. So it's very difficult to predict what's going to happen. And I think it depends who is launching what. I think maybe Elon might pay less attention to space weather, but you know, NASA will pay more attention. And you do get, I'm trying to remember the last one, but I remember seeing a launch was scrubbed. I think it's quite a few years ago now, but it was an event that I was looking at for my research for the Sun. And when I looked at the newspaper articles and what was going on, a launch was actually scrubbed because you could see the energetic particles. I think they even hit Mars. So it was just like, it was a no-go. So we do have to be careful, particularly I'm thinking, if we do get there, if we start sending humans into space again, then we're going to have to be really careful about the radiation, not just the radiation, say, that comes from these energetic particles and the eruptions, but also just generally the radiation. So I think people don't necessarily realise the amount of radiation you'll receive, even just on the journey to Mars, and then you've got to be on Mars. So it's quite impractical. Mars doesn't have a global magnetic field like we do. So I think these things might, depending on how far we get with this, because obviously, although we've got these massive dreams, who knows what's going to happen, but it's probably going to become more and more important as we send more satellites up there, as we rely on technology more, as we start sending. They had the issue, and their height wasn't far enough away for it not to be a problem, because if you've got stuff that's further up in the atmosphere or above the atmosphere, then it's not going to be an issue. So it was all to do with the timing, what height they were aiming for. I think it was quite a low height that they were at, so that's what made it problematic. And they increased the drag by like 50%. So, and they hadn't taken that into account, so that's why they had the problems. But you do, I mean, eventually satellites do come to their end of life and don't have enough fuel to combat atmospheric drag and eventually fall down anyway. But this was just unfortunate. If you're just sending a new satellite up there, you've spent how much, you know, millions of dollars, and then they come crashing down, particularly because it was about 40 of them.
Okay, so there's no more questions online. Last chance. Okay, well, everyone, thank you so much for coming to this talk. We've got a break for 15 minutes. There will be another talk in here in about 20-ish, so come back if you want to listen to that. But otherwise, thank you so much for doing that talk. That was absolutely amazing. Very interesting.
propulsion, I guess, originally?
Propulsion in Belfast, our manufacturing site working on Oxford.
The whole, like, innovation hub.
My base office is Bristol, but because I'm in the business team, I kind of end up going fairly.
I'm guessing around the UK.
Yeah, although I think Toulouse again.
We're meant to be in the new office. Which is frustrating, but it's why no one is.
Go around the front. Go around the front. We'll on to warm atmosphere.
So it takes long to get this stuff. I'll get notes in 5 seconds. It'll be like, anyway, read the problem. Cool.
You put practice to 5 minutes close. Add a correction factor after you practice it. Okay, take you 5 minutes. Yeah.
Yes, yes.
Well, I think You still take it?
Well, yeah. Oh, right. Oh. Yeah, the single stage. The single stage. But I thought that was fast. Yeah, so I thought whole rocking it up and then selling it
Definitely are, because they're tagging yesterday. I think that's what continuing training. Right, hello everyone. We can make our way into the room and quiet down. Got Stu and Tim here from Thales Alenia Space, 40 years experience as a company, designing some of the most famous satellite systems in the world, facilities all over Europe and the UK. So yeah, take it away, enjoy.
Thank you very much for that welcome. So I'm Stu.
I'm Tim.
From Thales Alenia Space. We call ourselves TAS for short because Thales Alenia Space is a lot to say. You should see my email address. So I had a look on Wikipedia, and apparently Thales Alenia Space is the largest manufacturer of satellites in Europe. Actually, in the UK, we're a relatively small team. We're about 250, I think, at the moment. But overall, the company size is a few thousand people. So first of all, big thank you to the organisers here for asking us to speak today. I got a few days' notice, and so I wasn't really sure what to speak about. So I decided to speak about something that I feel quite passionately about. You can see the title up here, Space Pollution. And this talk is really based on one that a colleague of mine gives. And in fact, I have a video sequence as part of this talk where she can speak to you directly about what she wants to say. Let's have a look at our first slide. So when I was a much younger person, space was really, in my mind, about being a frontier for mankind. It was all about science and exploration. And I think today it still is. You know, if we look at the Lunar Gateway project, for example, and our companies involved in building the Esprit module and also the HAB as well. So it's still got that theme, which is the thing that drew me to work in space. But it has changed enormously in the decades since I started my career, and it will change enormously again in the decades of your career as well. So today, the orbits around Earth have become a place where satellites deliver data for services for everyday life. So you may have checked a weather forecast before you came here. You may have used navigation to find the building. You may have done a bank transaction that relied on timing signals. All of these things, you may have just sent a message which you probably didn't realize went via a satellite network. And all of these things are going on, and you probably haven't realized how intrinsic satellites have become to everyday life through the services that they provide. But if the satellite stopped working, you'd notice. It would be a big, big problem. And so what's happened to the orbits around Earth is they've gone from being a frontier to being a resource, and actually a very precious resource, increasingly precious resource, as we come to rely on satellites to deliver services more and more. So today there are about, the number changes very frequently because some very large constellations are being launched almost continuously. But last thing I read was somewhere between 4,000 to 5,000 active satellites helping deliver services. And there's a few thousand historical derelicts and space debris. And that's really where I'm going with this, really. So, can we we go to the next slide? Who's seen a, we'll do this the old-fashioned way. Put your hand up if you've seen a picture like this before somewhere. That's really, really encouraging. And I really tell you why, because it was not until about, I think, 2012, and I've been working in the space industry since 2000, that in 2012 I became aware that actually there was a bit of an issue going on with derelicts and debris. I hadn't really paid any attention to it as a space professional. I've been getting on with my job, working mainly on satellite ground segments, and I hadn't really paid any attention to what was really going on in the orbits around the Earth. And around 2012, I got talking to a few people who started to talk about this topic, and it's become a fascination for me. And yeah, so, can you go back one, please, Tim?
Oh, sorry.
Yeah, so let's just explain this a bit. These sorts of graphs are produced from various interesting academic studies that are done, looking mainly at data, like NORAD data, for example, and running simulations and then producing these plots. So you've got the Earth there, and you can see around the Earth there's a really intense cluster of objects. And then it's not so obvious on here, but it's sort of marked in red. But there's an obvious cluster far out, which is, as you probably know, the geostationary orbit where most of the telecom satellites that we rely on are, the larger satellites. Not to mention some navigation and some weather forecasting stuff. And then you've got mid-Earth orbits, and then you've got an awful lot of stuff that's just moving through all of those orbits. There are animated versions of this, and it looks quite terrifying, actually. But you do have to remember that the volume of space is really, really huge. And these objects are not that size. They're actually quite small, many of them. In fact, this graph tries to represent what the 20,000 objects that we regularly track, or regularly tracked, which are about the size of your hand. In fact, one of those curious objects is a glove, an astronaut's glove, that was lost on a mission. Those 20,000 objects, that's just the tip of the iceberg. Below objects that size, which can be tracked, are smaller objects which can sometimes be seen, but not enough to be tracked. And many objects, very small objects, down to flecks of paint size, which simply can't be detected. And there are very wide-ranging estimates of how many of those are. And even a very small object can be a significant hazard for an active satellite that's providing vital services. Can we go to the next slide, please? So if you fire that ball bearing at that lump of aluminium at these type of hypervelocities, you can see the damage that's done. And satellites are nowhere near as sturdy as that block of aluminium. They're much more fragile objects. This is a fairly famous picture from ESA. It's the solar array of Sentinel-1B, I think, which is part of their Copernicus fleet, which is collecting data studying climate change. And they noticed a drop in power one day, wondered what it was, turned the camera around to have a look at the array and found there was a hole in it. And that was probably a little bolt, went straight through. Now, they were lucky. That didn't cause devastating damage. But the hazard to satellites is quite serious. And if we can't see the objects, we can't get out of their way. And the objects which are already there can collide with each other and we'll never know. And so the debris population increases. So I'm going to, before we press play, I'm going to introduce you to an inspiring colleague of ours, Sabrina. Sabrina came to visit us a couple of weeks ago. She couldn't be here today. So instead, we're going to show a film that was recorded last summer. It's just 9 minutes of a talk that she did in our hometown of Cannes. Sabrina was Female European Engineer of the Year 2019, and today she's head of in-orbit servicing and manufacturing for Thales Alenia Space. So she's a very senior engineer in our company. Let's see if this works.
Close your eyes. Imagine yourself outer space. It is completely dark, except for the distant glow of our beautiful planet Earth. As you open your eyes, you can see thousands of tiny bright lights orbiting our planet. They are satellites, tools that us Earthlings have put there to enhance our life from above. Satellites have become such an essential part of our daily life that we often forget how much we rely on them to make life run smoothly. They allow us to travel the world without getting lost in the middle of nowhere, most of the time. They observe and protect us by predicting the weather and monitoring climate change. But most importantly, they allow us to connect with each other by providing internet to the people in the remotest part of the world, even up in the skies when we are flying to our travel destination. Space has been providing us many ways to explore beyond our wildest imagination. Just like in science fiction movies, where fiction has become reality. For instance, let's visit our neighbor, the Moon. We are currently building a station around it called the Gateway, and in the near future, we foresee to build a moon village using the resources directly available there and relying on robots that we can either control from Earth or from this future station. This is how much space enabled us to achieve. If we come back closer to Earth now, as of now, we count 5,000 satellites around it, but only 40% of them are in operation. Why? Because the rest of them have become space debris. Not only has the number of satellites doubled over the last 3 years, but also the amount of space debris, which constitutes 60% of the existing satellites in orbit. More than 10,000 satellites are going to be launched in the next 10 years alone. Yet, there are already 34,000 pieces of debris bigger than 10 centimeters around the Earth. If we add to that the smaller bits, we can count more than 130 million pieces bigger than 1 millimeter. So if we add up the masses, we obtain the Eiffel Tower. It is like having a direct staircase to heaven. It is starting to look like a wrecking yard. If I were an astronaut, somewhere in my dreams, I would be quite scared to go up there. Human missions in space is already quite complicated. Space is already quite a hostile environment. But if you also have to dodge bits of debris or end up in a situation like the movie Gravity, where you see a piece strikes the International Space Station and everything going haywire, you can imagine how difficult it might be to perform any kind of operations in space. Besides, it also puts the existing satellites that we use to monitor Earth with in jeopardy. So, what can we do? We still need satellites, but we don't want to add up to the 60% of debris. So, space professionals like me are imagining new kinds of missions. These missions need to be smarter and innovative in order to first counteract the growing populations of satellites and better manage the future in space. Doesn't this look a bit familiar? It seems like we are reproducing the same mistakes that we have done on Earth, where we have done a lot of things very quickly without thinking too much about the consequences, and now we are trying to reverse back to a more sustainable lifestyle. What could be the solution in space? We have to do on-orbit servicing. It is a way of directly managing satellites that are already in orbit. A satellite, at the end of its life, it's either going to die in a graveyard orbit. This is the case for geostationary satellites, called GEO in short, that are at 36,000 kilometers in altitude, or they're either going to disintegrate themselves as they enter the atmosphere. This is the case for low Earth orbit satellites that are between a few hundred and 1,000 kilometers. A geosatellite is designed to last between 10 to 15 years. But if something happens, there's no way we can send an astronaut to repair it. First, it is very expensive, and second, also very dangerous. Besides, it will require more than 1,000 astronauts like Thomas Pesquet or Samantha Cristoforetti to perform these operations. We cannot really ask them that now, can we? So what else can we do? Usually, if something goes wrong, we call customer service. Well, we are not so far. We would need a special vehicle called a servicer. It's a super space vehicle with a robotic arm, various tools, gripper. First, it will inspect the environment of the client satellite, then perform a rendezvous to capture the spacecraft, and execute the required operations. It can be capturing it to help with its attitude, what we call station keeping. Could be refueling, repairing, or upgrading. A satellite, at the end of its life, as I said, for a geosatellite, they're going into graveyard orbit. So the servicer can also help the satellites reaching their end of life by putting them in a graveyard orbit, or for the lower satellite orbit, putting them back towards the Earth for them to disintegrate. All this helps us become more sustainable in space. First, if you attend to the satellite in orbit and extend their lifetime, you're delayed sending up a new spacecraft and to fully replace it in the future. And second, if you attend to the satellites that are reaching their end of life, you have less satellite that becomes uncontrolled debris. Thus, as a result, we become more sustainable. But in order to enable these advanced operations in space, could be refueling or upgrading, you need to prepare your satellites from now on with specific interfaces, like grapple fixture or interfaces that would require for refueling or upgrading. It is a bit more complex to perform it on an unprepared spacecraft. Still feasible, but more complex. Us humans always want to do bigger and better things. We like to run ambitious missions at an ever faster pace, but it's not necessarily in the most well thought out way, and reversing back is not always an option. We have entered a new era of space system, with an easier access to space, and where several mega constellations are foreseen to be launched to tackle the growing internet needs on Earth. So we are compelled to innovate, invent new technologies, and devise the smartest of missions to follow this trend. Or should I say, keep up as much as we can with this trend. This is the bright side of things, because in the end, we progress an amazing technology that will also be useful and applicable for future space exploration and for the benefit of humankind. Nonetheless, as we look forward to developing servicing missions, it allows us to take a step back, think, and be smarter about the way we exploit outer space to create a sustainable environment, following the path on what we are trying to do on Earth. After all, everything we do up there is for the benefit of us down here. So it's in all our interest to get it right. This contributes to life on Earth, to space for life. Thank you. Merci.
Let me introduce my colleague Tim.
Hello. So I am a propulsion engineer. So I'm going to talk about propulsion because these are all really great, as my colleagues alluded to, but it's not happening on its own. So we need to propulsion, and Thales is particularly good at propulsion. So just to start on the in-orbit servicing, there's a couple interesting challenges and benefits, just to expand quickly on it. Primarily, in-orbit servicing for defunct satellites, etc., is particularly valuable from a propulsion standpoint, because often in a satellite, it is not the payload that it runs out of life first. Generally, it's your propulsion system that will be your life-limiting factor. So to be able to offer to satellites that you can refuel them or just boost for them, or even take care of their end-of-life maneuvers to move them to a graveyard orbit, is a huge value and potentially can significantly increase the lifetime of your satellite, deliver the data, etc. It's been put out there to deliver. at a significantly reduced cost of launching a new satellite, at least. There are obviously some challenges around that. You have to get to the satellite that you're trying to service. If it really has run out of power, run out of fuel, then you need to get it under control. So they're not always cooperative satellites. Then you need to do its maneuvers, you need to refuel, you need to boost for it, etc. It actually requires quite a few different propulsion systems to do that. You need something with a bit of thrust to get it under control if it's spinning, but you want something pretty efficient to keep it up there, so electric propulsion-esque if you're doing that. So there's a lot of interesting propulsion challenges around that. There's also a lot of benefits to it, particularly around the geo market where you do have the heavier satellites with the high-tech payloads. That's where it really can add a lot of value. On the other hand, there is also the debris side of it, which I want to touch on, and that's more of an issue in our low Earth orbits, because that's actually where the majority of all these new satellites are going. The Starlink constellation, that's 42,000 satellites they're planning, which, considering we've only got 5,000 up there currently, is staggering. And if something goes wrong, or if anything goes wrong, we need to be able to remove it. So, current kind of agreement within the industry is that to even look at stabilizing the environment, we need to be actively removing up to 15 large objects a year from orbit. And that's not talking about the millions of 1 centimeter things, it's talking about the big satellites or second stages of launches, etc., that have been left up in space. Again, that is propulsion. It is obviously a concern because this image on your right is the hotspots of debris concentrations, and it's primarily, although it's probably hard to tell from that image, it's located largely in sun-synchronous orbits at the moment, because they're the interesting orbits, and therefore that's where a lot of the satellites in low Earth orbit have been put, and therefore that's where a lot of the debris is. And unless we start removing things, you encounter Kessler syndrome, which is akin to a fission reaction, kind of one bit of debris hits another bit of debris, which breaks up into 2 more bits of debris, which hit more debris and brown ones onwards, and you rapidly hit a point where you've actually ruled out sun-synchronous orbits for use in certain bands. So it's important, and it needs propulsion to do it, because clearly they aren't degrading or falling away on their own. So that's where active debris removal comes in. It is, again, very similar to in-orbit servicing. It is an aspect of it, so to speak, but different challenges. You need to have something that can, again, approach it, control it, because if it's truly is debris, you've got it spinning, it's out of control. And then you need something that can do a controlled deorbit on it. So you push it into the atmosphere quite accurately, which has a lot of different challenges to it, because, again, you need thrust, you need to control. You might even want to not fully remove it, but move it to a safer orbit. There's a lot of different challenges around that. But primarily, it's a big problem. So tackling it really is the only way to maintain the value and maintain the future possibility of a space economy. The tricky bit, of course, as many things is whose responsibility is it? Who pays for it? Which is a challenging question. It is one to be worked out, I think, as it moves forwards. But the agreement is that it needs to happen if we need to keep going to space, and propulsion is going to have to be pretty core to that. I'd like to do questions now.
Time for one, I suspect.
Yeah.
That'd be all right?
Yeah, I think time for 1 or 2 questions, if anyone has one. Like that.
Hello. Wanted to ask, what happens with the servicer that your colleague talked about after it has done its mission, because it's obviously quite expensive to put it in orbit, and if it has to reach geostationary orbit, it requires quite as much fuel. So it's more going to be a suicide mission for the module for that spacecraft as well.
It's a very good question. The architectures that we're kind of looking at are around having, these are very sophisticated spacecraft. The ability to rendezvous is very sophisticated capability, and then dock as well. So these are not cheap spacecraft to be able to do this reliably without actually having a crash and creating more debris, which nobody wants. So really, if we're going to launch these servicing spacecraft, they need to be able to do a lot of missions. Because it's not going to be sustainably economic to be able to keep one up, one down. That doesn't work. You need to be able to perform reorbiting or deorbiting or servicing missions on multiple clients in order to get value from your servicer. So it's, of course, itself got limitations. It's doing a lot of orbit transfers. It's got a very efficient propulsion system, but it's going to need more. So another whole part of this architecture is the ability to refuel itself, to provide an on-orbit propellant supply to the servicer so that it can continue operating for as long as it's safe to do so. And then, of course, once it gets to the point where it's starting to fail, you need to retire it. So it then needs to be put into, or passivated and put into an end-of-life state. Either in GEO, it's going to be out in a graveyard orbit, or in low Earth orbit, you need to deorbit it as itself. So it's quite a complex architecture. There's lots of different elements to it to actually make it economic. And this is an important point. If it's not economic, it's not sustainable. So we actually have to make a business out of doing it somehow. Is there any more time?
I think we're out of time,
okay.
Unfortunately.
Thank you so much, everyone, for coming to listen to us. It's been a pleasure.
Obviously, there's a TAS stand in the other building, so if you want to ask them any questions, or people from TAS any questions, feel free to go over there and do so for the rest of the day. So, yeah. Sorry? Just the first floor, the opposite building. Sorry, right. No, downstairs in the opposite building. Sorry.
Hello. Okay, we're about to start, so thank you for being here. If you need a seat, just grab one, otherwise we're going to start now. So this next talk is by David Sully, his UKSEDS competitions team lead, previous satellite comps lead. He is going to be doing a talk around the UKSEDS competitions and why you should get involved.
Hello, everyone. Yes, so thank you for the introduction. I'm David. I don't know how to get the slides on the main screen. Ooh, here we go. It will be solved in a second. But yeah, so I'll just tell you a little bit about the talk. So it's just going to be about all the competitions that we do here at UKSEDS. Thank you, Craig. So we have the kind of main competitions that we do, some new competitions that we do, and why you should get involved in the competitions if you're not already, and then a little bit about what sponsorship gets you in the competitions and why companies should sponsor if there's anyone in the room who's interested in that. So we'll start off, we've got 3 core competitions that we do. We've got the Olympus Rover Trials, the Satellite Design Competition, and the Orbex National Rocketry Championship. So these are the competitions we've been running for quite a long time. They're all kind of a year long, and I'll go into a little bit more detail about them all. So the Olympus Rover Trials, so this is about last year's competition. You can see what the teams have built there. It's sponsored by Airbus and RAL Space, and last year we challenged student teams to design, construct, and operate a rover for a habitat construction mission on Mars. And what that translates to is building a kind of quite a cool little rover. It's a lot of robotics, there's a lot of 3D printing, that sort of thing, and then they have to be autonomous. They can grab things, they can put them in different holes, and the challenges kind of change each year about what you have to do. And it's a really good competition. You get to go in, if you're in one of the finalist teams, drive your rover around on the Mars yard where they tested the ExoMars rover. So that's quite a cool thing to be doing. The satellite design competition is quite a similar competition. As you can see at the end there, there's a 3U CubeSat. So it's obviously not a space-faring CubeSat because nobody has the budget for that. But it's the smaller kind of robotics CubeSat. And last year we challenged them to do a CubeSat that could spin around a room and identify different points of interest. So different light sources that were simulating different things, different heat sources, and they had to be able to find out where they were in the room and what they were. And then this year, the challenge is to deorbit some space debris. And again, that's in an analog kind of environment where they have to grab a piece of debris and they also have to track it around the room. Then we have the Orbex National Rocketry Competition. So teams design and build a rocket to reach the highest apogee possible using a 29mm, I'm not going to try and pronounce that one again, 2-grain motor. So they're quite powerful, but not too big motors. So you can get into it fairly easily, but they're really good fun. This is, I think, one of our most popular competitions, really. And yeah, they're really, really good. We see teams do this all the time and getting some really great results. So it's a really fun competition to get involved with. So yeah, here's some pictures again of just some of the things that the teams get to do. It's a year-long thing, so as a team, our maximum size is of 15 people, I think, for all 3 of these. And so you get to kind of work around, do all different parts of the mission. Some teams structure it so that you have like quite a structured team lead and then different roles, or you can get involved in all different things, but you get to design and build and test them all, so it's lots of fun. So for this year, we've got 2 new competitions as well, which we've launched this year. We've got the Mach 22 rocketry competition. It's a bigger rocket, which is quite exciting, launching a CanSat. And then the in-orbit servicing and manufacturing competition, which is a bit of a mouthful, so we call it ISOM. And yeah, that's also a great competition. So yeah, Mach 22. These rockets, even bigger than before, they launch a CanSat, which is a satellite built to the size of a Coca-Cola can. And they go 2.5 kilometers in the air. And this is in partnership with the Mach 22 event, Discover Space and UKLSL, which are all great. And it's, yeah, that's quite a fun competition as well. Very, very big rockets. The in-orbit servicing and manufacturing competition is entirely report-based. It's still quite exciting. As you can see, there's a lot of people involved. So in collaboration with Satellite Applications Catapult, students design their own missions related to in-orbit servicing and manufacturing. So you just heard a little bit from the previous speakers about in-orbit servicing and how important it is. You can imagine all of these people are really interested to hear what ideas you can come up with in your reports. So you've got to justify your mission proposals from both a business and an engineering perspective, which is one of the more unique bits of this competition. And then, yeah, you get to do a Dragon's Den style scenario to kind of these sponsors and things. It's very exciting. So what do you get from the competition? So here's a list of skills. I'm sure you see these a lot at university and things, lots of soft skills. So there's teamwork, project management, problem solving, systems engineering, and specialist technical knowledge. So obviously the technical knowledge side depends on which competition you do. A lot of it is quite themed around robotics and coding and that sort of stuff, so they're really good skills to learn. But not only do you get to kind of practice and demonstrate these skills, we also put on workshops that you can attend from our sponsors on different things. So recently, all of the people competing in our competitions had a system engineering workshop from professionals at Airbus who've been doing systems engineering for real space missions for the last 30 years. So there's some really good ways that you can kind of show your learning and demonstrate it. So yeah. Same again, really, on this side. So developing and demonstrating ideas and skills with feedback and guidance from experts. So you get an industry mentor when you're doing your competition for the rovers and the satellites competition, as well as for ISOM. So you get someone who is partnered with your team throughout the whole year who will give you feedback on your designs, on your work. And they are an amazing source of networking and an amazing source of information. They won't give you feedback saying, oh, move this bolt here, move this bolt there, but they'll say, you're on the right track. Think about this company, go and do this. And there's someone who has already been in the industry for a long time, and they can really help you kind of guide what you want to do and give you more information. And yeah, making connections with mentors for your future careers. I can't stress how important this is. A lot of the time we see teams not communicate with their mentors as much as they should be. When I did the competition, my mentor invited us out to Los Angeles to visit them, and we got to go and visit SpaceX. We got to go and see the James Webb Space Telescope. I'm not going to promise that that's something everyone will get, but if you really make a connection and work really hard, then your mentors they're doing this for fun, and they will give back as much as you give them. So the timeline for competitions, so people who haven't done it before, they launch in October. The registration deadline's in November, so you have about a month to form a team once you know what the challenge is going to be. We release all of that information on the websites. And then in December, January time, depending on your competition, you get the preliminary design review, and then you get March, April, the critical design review, so that's more of a detailed report. Test readiness review, so the competitions where you have to build something, you have to kind of prove that it's going to work and that you've tested it, and that's in June and July. And then the competition days we tend to do in July and August, depending on what competition you're in. The rocketry is slightly different. They don't have kind of a formalized day as much. You can launch on your own if you want to, but they also do try and encourage people to come together if they can. So what support is available? I've already talked about the mentors, so you get your mentor guidance. You get match funding, so we give teams, in satellites, as an example, £250 if they raise £250, so we match their budgets. Marking and feedback from professionals. So your reports will be marked and you'll get feedback from professionals. So the people you saw sponsoring the competitions, they provide reviewers for us, and they will read you through your work, and they will tell you kind of how to improve, what needs to change, and that sort of thing. It's not kind of a harsh marking. It's there to kind of help you grow and learn what bits you might need to do more on. And we can put on workshops and things as we go through to help you develop in those areas. And then there's the Orbex Gender Diversity Grant, which we have a slide on here. So this is for any teams that have 50% female or non-binary members. And it means you can get a cash grant for your team. And it varies a little bit depending on which competition it is. But yeah, this is a great resource. So if you are in the competitions at the moment and you have 50% female or non-binary members, then please send us an email to your competition. Or if you're thinking of entering with a team, then please do, because it's a great resource. It's a great way to support you in the competition. So a little bit on how they support the sponsors. So we had, even in 2021, with the pandemic, we had over 170 students complete one of our projects. That was only those 3 core projects that we had going then. And so despite the fact people couldn't meet up to build properly, we still had that. So we get a lot of students every year engaged with the competitions for the whole year, which is great, and across a range of STEM degrees across the whole of the country. So you can reach students across the entire country, across lots of different disciplines. The competitions, the sponsors help us to decide what we're going to do with the competitions. So what skills we're going to help students develop, and that's based on what skills the industry needs. So when we're defining the challenges, the sponsors help us work out, okay, we need some coding, or okay, we need more people to learn about AOCS systems, or things like that. And that way, when you do the competitions, it makes you so much more employable, because the companies have said what skills they need, and then you can demonstrate that you have those skills and that you've done it for a whole year. So yeah, I'd also just like to thank all of our sponsors for the competitions across all of them. They're amazing. They provide us not just kind of support with financially, but with people and time and so much more. So yeah, they are amazing, and I can't thank them enough. But yeah, if you want to keep in touch, you can be a member of UKSEDS. I'm sure lots of you are, as you're already here. But you can subscribe to the newsletter. or you can join your local branch. And if you want to join the UKSEDS team, keep an eye on Space Careers, or you can sign this QR code. I'm sure it will be around in other places. Or if you go on the competition websites, then there will be an email address there. If you're interested in an individual competition, you can find out more on each of their websites. But yes, thank you very much for listening. Sorry it was a bit of a fly through an overview of competitions. You can find out a lot more on the website, or you can talk to me at the end, or we might have some time for questions at the end, hopefully. But thank you very much.
Thank you so much, David. That was a great talk. This next one is going to be by Joanne Oliver. She is a business analyst for Space Careers, focusing on the redevelopment of the careers website. This talk is going to have tips and tricks for how to get your space career.
Hello. Okay, thank you very much, Hannah. So I know you've been listening a lot this weekend, so I kind of want it to be a bit more interactive. So I'll just ask you to get up Mentimeter. You might have used it in class. So you can just type it into Google and get it up, and then put the little code in the top there, and it'll take you to my little quiz. And while you're doing that, I'll introduce myself as well. I didn't realize the icons could come up. So yeah, the web address is at the top, and the code is 41927583. Thank you very much. Just wait a little bit longer for you to get on. Okay, all ready? Perfect. The talk today is just going to be a quick stop of space careers, so I'll just go through some careers advice and things like that. So I've got a few quick questions to answer, and then I'll go through the answers. Okay, first question. What is the best thing you can do when you don't have all the experience an employer needs for a job? So tailor your experiences, say you don't have the experience, or just don't apply altogether. You have 20 seconds left to answer it. There is no right or wrong answer, but it's what you think would be the best thing to do. Okay, finishing up. Oh wow, there's quite a lot of people online. Perfect, yeah, so that's the one I was aiming for, tailor your experiences. So yeah, say you don't have the experience, I'll go over that, but tailor your experiences basically is, I'm sure you already know because you already voted for it, but if you don't have the experience they need, use something that you've used previously. If you're coming in early careers and you don't have anything, use whatever you've got. So if you've done sports clubs, something like that, something that will apply to what they're asking for, you can always tailor it and adapt the language that you're using in your CV, in your cover letter, to be able to get what they need from them. It's especially important in early careers because you're obviously not going to have a lot of that experience, so they're almost not expecting it to be exactly what they want. It's a little bit different for when you get higher into mid-careers. Obviously, you do need a lot of experience, and with technical roles, it can differ. But it's just a really important thing that whatever they're asking for, you can kind of tweak your answer so that show them what you can give them, basically. Okay, next question. Hopefully you get this all right. Okay, what do employers love to see on CVs that candidates do not necessarily need to have? So a driver's license, extracurricular involvement, or animated GIFs? My personal favorite. Okay, you have 20 seconds left. Ten seconds. I know which one you guys are going to go for. It's pretty easy. Yes, perfect. For all the ones that selected animated GIFs, I'm really curious of which ones they would be. Please send them through to UKSEDS Instagram so we can see them. So cat GIFs would probably be my go-to, or some kind of animal thing. Anyway, so yeah, extracurricular involvement. So a lot of involvement with UKSEDS, competitions, as David was saying. Employers love that. We've spoken to a lot of our employers who advertise on our site, and they're always saying how much they love it, seeing students getting involved in different things, especially across the sector or maybe in different sectors, doing something out of the ordinary, not something that not everyone else does. So if you've got your degree, everyone's got a degree these days. It's just doing something which gives you those extra skills, but also employers look at you differently and they see a unique personality back on your CV. If it's just a blank paper, you've got lots of things to put on there because you've got involved with all of that. And last question. Which of these skills do you see as most useful for your career in space? Python skills, salsa skills, or soft skills? You have 20 seconds left. Ten seconds. I feel like it's a bit too long. Ooh, interesting. Okay. So yeah, I put Python skills in there because I feel like a lot of us have heard that want to learn Python or have already learned Python. So it is a really interesting one. But the one I wanted to pick up on is soft skills. So this is something that came up in the skills survey that the sector is doing at the moment. There's a lack of soft skills in the industry. So this is things like time management, teamwork, presentation skills, bid writing. They might not always teach you this at uni, especially if you've got like a technical degree. They might not always teach that. And as much as you guys might not like group presentations, they're really valuable for your soft skills, and that's kind of what's lacking in the industry at the moment. So when they do give you group work at uni and things like that, it's actually really good for you. And different things like extracurricular involvement, like I already mentioned earlier, is really good to develop these soft skills as well. So pretty much anything that you can get involved with helps develop all these skills rather than all the technical ones you've got, like Python skills. Salsa skills are also needed because that's just to have a bit of fun. Also, Jacob, who's coming on next, is really bad at salsa, so I just thought I'd put that on there. But hopefully he won't show you that. Okay, and the last one is a little word cloud. So I just want you to type in now, what careers resources would you benefit from on spacecareers.uk? So that's our website. So depending on what level of education you're at, is this CV writing skills or is this something that you need help with? So yeah, just pop them in and they'll all come up on there. Memes. Oh, our UKSEDS volunteers have become really good at making memes. So on our Instagram page, I think we've got a lot of that NSSC. Salsa skills. There's so many different salsa clubs in London I can recommend. Yeah, people skills. That's a very big remit, people skills. But events like this is amazing for people skills because even if you're introverted, like me sometimes, you just have to go for it and introduce yourself and network. Events, definitely, we need more space events. Oh, there's so many, thank you. Mentoring. Yes, there's a lot of mentoring programs out there, but generally it's good. Oh yeah, okay, this is all good to know. So for this one, we do have a Space Careers stand in the Careers Fair up the top. If you've seen it, just come along and we'd love to chat about that. We really want to help you guys get into the industry. We want to launch your career for you. So if there's anything that we can help you with, please don't hesitate to get in touch. So you can continue adding them, I think. Okay, perfect. So just quickly, 5 minutes. I did that presentation because we are the Mentimeter because we're part of Space Careers. So we are under the remit of UKSEDS. We're all volunteers as well. We created this site in 2015. So this is pretty much what the site looked like. Can I have a show of hands that who's already been on this site? Oh, amazing. That's what we like to hear. So this is essentially a one-stop shop for early careers. We've got careers resources, job advertisements on there. You name it, we want to have it there. So events, news, everything. So like I say, it was launched in 2015. At the moment, we have about 375 employers advertising on there. From massive Airbus companies to small startups. They love using Space Careers and getting students. But we have everything from internships to placement roles, graduate schemes. It's all on there to get you into the industry. So it's mainly for early careers, so 0 to 3 years experience, and space only. But we really do want to branch out as well and not just have engineering, not just have the technical side on there, but we want to be able to bring in business side of it, the art side, lawyers, policy, journalism. That's all needed in space. So it's important to note that we're not just focusing on these technical popular ones in the industry. We're actually trying to engage with other employers from different sectors and drag everyone in from there into the space industry. And yet, lastly, careers resources, which I'll just mention now. So if there's anyone here that's pre-university, so you're at secondary school or you're at college, we have courses on there. So kind of going through what courses you might want to choose at uni for where you think you're going. General advice on directions if you need some help. That kind of thing, getting you ready for the next steps in your education. And then for university students, it focuses on more like CV skills, cover letter writing. We've got a day in the life that we want to do. We're going to do a lot of takeovers and reach out with employers and get them to do maybe a day in the life so we can see what their roles are like. Just to really show you a whole breadth of what's going on in the industry and how we can help you get a job. So that's pretty much Space Careers and a whistle-stop tour. I do have a QR code on there because we are currently redeveloping the site. So we want to expand it even more. So if you could scan that now or come to the stand later and chat to us about it. There's a survey there, and it's basically like the word cloud, but more extensive. It will take 5 minutes, and if you could fill it in and just tell us what you want to hear. We're really open to ideas, and we're here to help you, basically. So whatever you need for resources to get your jobs, we'll help you with it. And a little bit to add that there is a £30 Amazon voucher on there if you win. So enter your email at the end, and we'll do the draw in a couple of weeks, and we'll let you know. But yeah, thank you very much for listening, and I'll hand you over to the next speaker. Thank you.
Amazing, thank you. Another great talk from the UKSEDS team. This next talk will be by Jacob Smith. He is the founder of Space Projects UK, connecting students with the space sector during your degree so you can get experience. His talk is going to outline the process and how you can get involved.
Hello, is that working? Cool. Hello everyone, my name is Jacob. Quick background on me, I was the chair of UKSEDS last year and I set this scheme up a year ago now. I just want to give a quick overview. It's all about matching students doing their final year projects at university or master's projects with space companies. So we've known for quite a while that graduate recruitment in the space sector is not plain sailing for students or employers. Employers often struggle to find students with the skills that they want them to have, and students also struggle to get the skills that the employers want. So what the idea is, oh my God, is that me? It can be really hard to get the experience as well. Extracurricular activities are a great way of getting these skills. However, they're often quite competitive and they're not inclusive to everyone. So what we really need is like an inclusive way of providing experience to students before they graduate. So the scheme basically matches students with the company. So we've set up a framework, and the idea is that companies submit the projects to us that the company wants to do. And then we will advertise them on the website. All the students can go and look on the website. Submissions can come in all year round. And then you would apply through the website to a project that you're interested in. We can deal with the applications. We facilitate the applications between the students and the company. And then the company will make the final selection of the student. And you can start your project. You get supervised by a supervisor from the company. You get to do a really cool project. You also obviously have your academic supervisor from your university. What's really key, if you're interested in doing this as a student, is to really start finding out about how your project module runs at university. So this is for any discipline, any student project, so individual or group project. And we've had 7 projects in the last year, which I think I might show. We're really running short on time, so I'm going to just skip through some of these and just kind of outline. Obviously, the benefits, you get to work on a space project, you get some new skills, you get to kind of get insight into the company and the way that they work, get some space-specific experience, and that's great for your CV. And you kind of get to show, get some job insights as well. And some of the companies that we've got our projects with running over the last year are already thinking about hiring some of the students that they've had. In case there's anyone in the audience who is interested from the company's perspective, some benefits include time for students to work on projects for you that you don't normally have the time to explore. It's also free for the company because it's part of the student's degree, so there's no salary required. Increased innovation, better recruitment, as I was talking about, and new ties with universities. How it works. So as I said, undergraduate master's projects. I'm just going to skip through these, unfortunately, because I don't want to keep you from lunch. The key thing is lining the project up with the intended learning outcomes of the project module. Companies don't always have 100% of an idea of what that means, so we've kind of created a framework structure for them to follow that makes sure that it will match what your project module lead requires of your project. You also have to find a supervisor, someone who would supervise you if you were successful in the application. So you need to get on thinking about this quite early. Projects will be coming in over the next few months to start in September or October next year, or later this year, sorry, next academic year. All the information is on the website, so the website is spaceprojects.uk. I think I've said most of this. Oh, that's messed up. Some of this year's projects, I'm just going to flick through some projects we've had over the last year. I think we've had 7, 1 group project and 6 individual projects. Is anyone in the audience one of the students by any chance taking part? I can't see any hands. No, I wasn't expecting you to, but it would be nice to meet you. So yeah, this is just an example of some of the projects. You might recognise some of those names, you might not recognise some of the other ones as well, so it's a nice opportunity to learn about some new companies as well. And I just want to finish by saying thank you to our supporters as well. The ESA Business Incubation Centre, the Satellite Applications Catapult, UK Space Agency, and the South Coast Centre of Excellence in Satellite Applications. And these are really supportive of the scheme, pushing the scheme to their network so we can kind of bring in as many companies, make as many companies as possible aware about the scheme so we can provide more projects to you lot. So I don't know if we have time for questions, but I'll stay around down here if anyone has any questions afterwards. Thank you very much.
Yeah, so we definitely don't have any time for questions because lunch started. But just a quick announcement, the arts panel that's after lunch has been moved to the coffee room. So if you want to go to that, it's a great event. But yeah, check the rooms. The team's going to be around all day, specifically near the UKSEDS Space Careers and Space Projects stands upstairs in the other building. So if you want to have a chat, go ask them. You can also send us an email too. Thank you for being here.